Hey AP Advanced kids, in today's video I want to talk a little bit about different capacitor configurations. Now before we do that, I want to just talk about a couple of different scenarios and what happens to the charge, the electric field, the voltage, and the capacitance, because these are great multiple choice questions. So let's take a look at this capacitor. We have charged it by attaching it to a battery, so it currently has a voltage across it that's equal to the voltage of the battery. And then what I'm going to do is I'm going to disconnect it from the battery, and then I'm going to pull these plates apart. So before maybe they were some distance d, and now let's say I'm super careful when I pull them apart, and now I'm at a distance of, we'll call this d nu, which is greater than d. So if you think about it, right, once I disconnect the battery, as long as I'm super careful pulling those plates apart, the charge is stuck, right? It has nowhere to go as long as I'm super careful. So that means the charge stays the same. Well, if the charge stays the same, then the electric field should also be the same. Because remember that the electric field equation for parallel plates, and not that this would be different for other scenarios, but the electric field for parallel plates is Q over E naught A, right? I didn't change the area of the plates. I just separated them a distance D. So if this is the same, then the electric field also must stay the same. So if I don't change the charge, the electric field's the same. But what about voltage, right? It's not connected to the battery anymore. That baby's gone. Well, if the electric field is the same and I change the distance, that means I have to change the voltage, right? Because we have the equation that the voltage across a parallel plate capacitor is, well, across anything, right, is the negative integral of E dot dr, or in the case where we have a uniform electric field like these parallel plates, E times d, or the distance. So if d increases and the E is the same, that means that the voltage difference has to also increase. So because of this equation, our voltage is going to go up. Whoa, that's totally cool, right? Well, where did that voltage come, right? Voltage is the potential, or electric potential, right? That's the potential for energy. Well, how did I just make some energy? Well, it's because I did work, right? I did work and I pulled those plates apart. So I put some energy in to the system by doing that, and that's why the voltage goes up. Well, what about the capacitance? Does the capacitance change? Well, remember that our capacitance equation is Q delta V. Well, at least that's one of our equations, right? So this Q stayed the same, right? This is same, but this increased. So that means that capacitance must have decreased. Now, you're probably like, Mrs. Campbell, you said in the first video that capacitance is dictated by the geometry of the capacitors, and I shouldn't think of capacitance in terms of this equation. Fine, fine. Let's go to our capacitance equation for parallel plates. The capacitance is equal to E naught A over D. What just happened? Area didn't change, right? But D increased. So guess what? It doesn't matter how we look at it. Capacitance goes down. Pretty cool, huh? Well, what if we left the battery connected? So what if we charge the capacitor and keep it connected to the battery and then carefully pull the plates apart? Well, now let's start with voltage, right? Because it's connected to the battery and the battery dictates the voltage is still the same. It still is equal to the voltage of the battery. I'm going to call that VBAT. Well, that's interesting. If the voltage is the same and I pulled it apart, doesn't that mean the electric field has to change, right? Because voltage is equal to a negative E dot dr, or ED in this case, because we're talking parallel plates. So if voltage is the same and D went up, right, that means E, the electric field, has to decrease, right? Because it has to equal the same voltage. And remember, by our equation for parallel plates, the electric field is Q over E naught A. If electric field has decreased, that means the charge has to decrease. So some of this charge must actually just leave and go back into the battery. So we're going to get some electrons, right? They're actually electrons. They're going to actually head out and be like, sorry, dude, I got to go. Well, if I lost some charge, what happens to capacitance? Well, again, capacitance is Q over V. So V stayed the same, but Q decreased, so that means C decreased. And like I said, it's dictated by the geometry of the capacitor. And so if we go back to our original equation there, over D, if D increases, then C decreases. So either way, we can prove it. So pretty cool, huh? Some interesting stuff about capacitors. Great, great multiple choice questions. Hint, hint, nudge, nudge, wink, wink. All right, let's talk about putting capacitors in different configurations. So one configuration is we could put them in what's called parallel. So you'll see they literally are in parallel, and it's like they're in different branches. And so if we connect, maybe some sort of battery here, this is the voltage of my battery, we'll call that VBAT, right? The voltage of the battery is going to feed each of these capacitors. So we're going to deposit charge, onto each of these plates separately, and that's going to kick off charge, an equal amount of charge, which is going to, end up going back to the battery. So I can fill up each of these capacitors with the amount of charge their capacitance dictates. So the voltage, and when I'm in parallel, the voltage across each of these capacitors is going to be equal to whatever it is that I charged it with, whatever my battery voltage is. Now, the total charge that I put on the capacitor, the total charge I took out of the battery to store on my capacitor, then is going to be a sum of each of these individual charges that I put on the capacitor. Now, if we go back to our capacitance equation, because what I want to know is, well, how does that affect capacitance? Well, we have our capacitance equation, right? Capacitance is Q over V. But what I want to do is I want to plug it into this equation. So I'm going to rearrange it and call it Q is equal to C times V. And so we're going to call this the total. So we're going to call this the charge total, and instead I'm going to put in this. So the capacitance total times the voltage, which, right, is just the voltage of the battery, is equal to the Q1. So that would be the capacitance one times the voltage of the battery, plus the capacitance of the second one times the voltage of the battery, plus the capacitance of the third one times the voltage of the battery. And since the voltage of the battery is the same for all, we can cancel that out, and I come up with the total capacitance. So when I put capacitors in parallel like this, and I can feed electrons to each capacitor individually, I increase the total capacitance. It's like I took these capacitors and I just stuck them together, so the area increased. So we say that the total or equivalent capacitance, that's what EQ is, the equivalent capacitance, is the sum of each of the individual capacitors. So the more capacitance I want in my circuit, the more capacitors I add. What about if I put them in a line? So if I put them in what's called series, so in series, then they're all in the same line. They're like in the same wire. And so if you think about what happens, right, because electrons we follow positive charge when we do circuits, which will be our next unit. But really what we're doing, right, is we're loading electrons. Electrons are free to move. So we're going to put an electron on this capacitor, which is going to knock an electron off this capacitor, and it's going to get stuck on here, right? These are not, there's no ability for the charge to jump between the plates. And so we're going to load charge on there, which is going to knock an electron off of here, which is going to deposit on there, and it's going to create this repulsive force that knocks an electron off of there. And this process is going to keep going until we have loaded as many electrons as we can. But because of that, because of the scenario, the total charge has to be the same on each of the plates. So whatever charge comes out of the battery is the same as the charge on the first capacitor, which is the same as the charge on the second capacitor, which is the same as the charge on the third capacitor. Well, that doesn't sound very efficient, does it? And if we think about the voltage, right, this time the voltage across this battery has to supply all of these capacitors, which means it can't just give, remember, this is the potential for energy, and I can't just create energy out of nothing. So that means that the total voltage, or the voltage of my battery, has to equal the sum of these voltages. So when I add those voltages together, I'm going to get the voltage of the battery. So if we go back to our capacitance is Q over V equation, and this time we rearrange for V, we get Q over C. So if I go here and I plug this in, the total voltage, which would be the total charge over the total capacitance, is equal to the charge on one, which is the same as what come off the battery. I'm going to call that BAT because it's really what came out of the battery, over the capacitance of one plus the Q on the BAT, right? Same charge, no choice, always dictated by the fact that these are in a line and I'm limited because I can't have electrons just jumping. So I end up with this really interesting equation because these are the same, so we can cancel them out, and we get that in series, the reciprocal of the total capacitance, so this is my total capacitance, is the sum of the inverses of the separate capacitance. So another way we could write that is the inverse of CEQ is equal to the inverse sum of all of the inverses plus blah, 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 blah. So the inverse sum of each capacitance is equal to the inverse sum of the total capacitance, which we call CEQ. The sad part about this means that if I put them in series, I'm going to actually reduce the amount of capacitance I have in my circuit. And now you may wonder, well, why would you want to do that? Well, sometimes it's handy to have less capacitance than you have the capacitors for. Maybe you need a certain amount, but you don't have a smaller capacitor. Well, you can put some in series and do some math, and you could get the capacitance that maybe your circuit needs. So anytime we put capacitors in series, it decreases the total capacitance of the circuit because I'm stuck. Right, I'm stuck, and capacitance is equal to the charge over the voltage. So I have the same amount of charge on each of my capacitors, but my voltage is less than the battery. So I end up with less capacitance. Now, just a little summary. When we talk about series, we're talking about capacitors. I like to say they're in the same wire, but they're like in the same sort of loop. In parallel, they're actually in different wires. The voltage in series is different for each capacitor, unless they're, of course, the same capacitance, but it's the total sum. Each voltage shares some of the voltage of the battery, whereas when they're in series, the voltage is the same for all of them. The charge is the same when we're in series because there's no other place for the charge to go. So whatever charge I put on one plate is how much charge goes on the next plate, which is how much charge goes on the next plate. But in parallel, they're all different branches, so the charge can just fill up the capacitors based off their capacitance. The total capacitance in series decreases because I'm limited by that charge and I have to share that voltage, whereas in parallel, the capacitance increases. All right, so those are some cool things to know about capacitors. The last thing I want to talk about is energy stored in a capacitor. All right, capacitors store charge, which means that they give us the potential for energy, kind of like a battery. All right, a battery does work to put this charge on these plates, where they get stored because they can't move off of there. And then when I disconnect it from the battery and I connect it to another circuit, now the charge is going to flow until that potential is zero. So there has to be work done to move this charge from one plate and knock it off the next plate. But as you can imagine, as we add charge, right, that repulsive force is going to increase. So the work that we have to do every time we add another charge to the plate is more, right? It takes more and more force, which means I'm doing more and more work every time I have to put a charge on the plate. So As the voltage increases, the amount of energy that we're storing increases. And so if we think about it in terms of the change in, or the amount of energy stored, the electric potential energy here, right? The electric potential energy, if you remember, the electric potential energy is equal to Q delta V, right? Or the negative of work. And if you remember our capacitance equation, right? Capacitance is Q over V. So if I rearrange this, and that should really be a delta, if I rearrange this for voltage, right, then I get that the voltage is Q over C. So I can plug this in here because what I want to do is I want to integrate how much charge. I want to add up all of the charge that I need to add to this plate. And so if I plug that in here, right, then I get this, that the electric potential energy is Q times dQ over C. C is a constant, right? So we can pull that out and we'll do an integral from 0 to Q, Q being the total charge that I added to the plate. So if you imagine that the integral, right, of Q dQ would be Q squared over 2, right, from our 0 to Q. And so 0 would just be 0. And so that's how I get this equation right here. So the energy stored in a capacitor is equal to the work that I do putting charge on the plates, and that's equal to Q squared over 2C. Now, of course, I can use this equation. Say I didn't have the capacitance, maybe I had the voltage, right? I could put this equation in there, and we would get 1/2 Q delta V. Pretty cool. Q delta V, 1/2 Q delta V. Wow, that almost sounds like this equation with a half in it. Interesting. Many forms of energy. All right, so where's this energy stored? Well, the energy is stored in the electric field. That's what we say, right? Anytime we separate charge, we are creating potential energy, electric potential energy, and that energy we say is stored in the electric field. So because it's like this half thing, right? This half Q squared over C, or this half C times delta V, right? It's kind of like, if you remember back to spring potential energy or elastic potential energy, it's kind of similar, right? Remember that elastic potential energy or potential energy of spring for a simple spring was 1/2 kx squared. So it's kind of similar in that as we stretch a spring, right, we increase the potential energy because the force increases as we stretch it or compress it. And it's kind of the same thing with capacitors. So as we store energy using a capacitor, we have to do more work. There's more force to deposit those charges. So pretty cool. All right, enough of this. Do your WSQ and I'll see you in class.